Hello everyone, my name is Jason Russell from Capstone Team GT20, and today Ben Zabick and I will be discussing the design process and technical details for our team's final combustion chamber design for the Yellow Jacket Space Program's YJ-1S rocket engine. I will start by reintroducing you to our project and remind you about some of our goals and requirements. Then I will briefly discuss the selected design concept that was previously developed along with some supporting analysis results. My colleague Ben Zabick will then talk about the design details associated with the final combustion chamber, nozzle, and coolant delivery system designs. He will also discuss a performance evaluation for the final design, as well as our conclusions and potential future work. The Yellow Jacket Space Program, or YJSP, is a student rocketry team at Georgia Tech that we are developing the combustion chamber design for. Their current engine, known as the YJ-1S, is a liquid bipropellant engine that was designed and prototyped to provide thrust for a future amateur rocket. While this engine is capable of producing the desired thrust, it is not suitable for flight due to its large mass and limited operation time. In an effort to progress with their rocket design, YJSP has requested our team to design a new combustion chamber that is more suitable for flight. The goal of this project is to design a new combustion chamber for the YJ-1S that will meet the YJSP's requirements. Their performance requirements demand that the new combustion chamber should weigh less than 5 kilograms while enabling the YJ-1S engine to fire for at least 10 seconds without failure. In addition, the performance parameters associated with their existing design, such as thrust and specific impulse, may not deviate by more than 5%. In terms of actually manufacturing and assembling the new design, YJSP requests that the design yields a material cost of less than $1,000, and it must be manufacturable by students at Georgia Tech facilities. Previously, design concepts that involved ablative, phase change, and regenerative cooling techniques were evaluated and weighed against each other to determine the most appropriate design approach. It was determined that a regenerative cooling system would not be an effective solution due to the excessive mass that it would require. Also, the use of an ablative cooling system would require the addition of an ablative layer on the inner chamber walls that would negatively affect the overall performance of the engine and would also be too expensive to maintain. For these reasons, the concept of a phase change cooling system design was selected as a potential design candidate. A conceptual design that employs a phase change of water was then developed. While this design requires several expensive manufacturing techniques such as roll forming and metal spinning, its low mass makes it a feasible candidate for the final design. The feasibility of the design was then tested by developing and analyzing a thermal model of the chamber wall. The convective boundary conditions for that coolant side of the chamber wall were governed by the various heat transfer coefficients associated with each boiling regime. The variable heat flux used in the model was determined through the use of Bart's correlation and NASA's chemical equilibrium analysis code. An FEA of this model was then performed over a range of chamber wall thicknesses so that the wall geometry could be optimized. The results of the FEA suggest that the cooling system will be the most effective if the combustion chamber wall is approximately 0.2 inches thick. While the maximum wall temperature can be minimized, the FEA results actually revealed that the wall material at the nozzle throat would fail under even the most optimal conditions. These results do not invalidate the design as a whole, however, they do suggest that significant changes need to be made to the nozzle so that the heat load can be supported.
To deal with extreme heat loads, ablative cooling, where the material flakes off a small amount to remain cool, was selected because it has low mass and can be easily manufactured. Graphite was selected as the ablator material. Graphite is low cost compared to other ablators, has decent ablation performance, and has been widely used in other rocket nozzle designs. Although graphite is relatively weak, it has sufficient strength to easily handle the stresses from combustion gases. Because of this, the dimensions of our nozzle were actually driven by how thin the part can be turned during machining, to the brittleness of the material. From this, a wall thickness of 0.27 inches was chosen. The ablation performance was analyzed using Fiat V3 software from NASA. From this analysis, the max radial ablation depth over the engine burn was found to be 13 thousandths of an inch, and the max temperature reached by the nozzle was found to be 2011 Kelvin. With this information, the interface between the nozzle and chamber can be designed to handle thermal stresses. Here you can see our final chamber design in cross-section and exploded view. The design consists of a welded titanium injector plate and cooling jacket wall, a titanium chamber wall, and the graphite nozzle. The entire design is easy to disassemble for inspection, has minimum welded connections to reduce cost, and can be manufactured at Georgia Tech facilities, with the exception of the welds, which must be done by a professional welder using specialized equipment. Zooming in on the top of the chamber assembly, we can see the interface between the chamber walls and welded injector plate / jacket wall assembly, which was designed with a threaded connection that seals using a graphite gasket. This allows the chamber to be disassembled for inspection. The injector plate features an angled cavity which ensures there is only a single high point in the cooling jacket where the steam collects, and the vent port is placed at this high point. The threaded connection requires 379 foot-pounds of torque to maintain a seal. The interface between the graphite nozzle, combustion chamber, and cooling jacket was complex due to the differential thermal expansion between each part. To compensate for this, a floating radial O-ring seal was used at the base of the cooling jacket, allowing the parts to move relative to each other but maintaining a seal. The graphite nozzle is held in with a stainless steel retaining ring, which handles thrust loads and can be easily installed and removed. The interface avoids thermal stresses from the neighboring titanium parts due to titanium's greater coefficient of thermal expansion. The interface between the graphite and titanium is sealed using a low-cost, high-temperature sealant compound. Finally, the bottom of the combustion chamber assembly has 4 square tangs on it, which allow a water-jetted steel plate to be installed, which can be used to torque the threaded connection at the top of the assembly using a torque wrench. The coolant delivery system is replenishes the cooling jacket as water is vaporized and vented to the atmosphere. The system consists of a coolant jacket, which is pressurized before the engine fires, and there is a flow control orifice which ensures water enters the cooling jacket at the same rate it is vented. In order to size the system and determine the required tank pressures, orifice sizes, and volumes, the system was modeled in MATLAB with results from previous thermal FEA models determining the rate at which steam is generated. From the MATLAB model, it was determined that the tank required an initial pressure of 60 psi for sufficient flow throughout the engine burn, and that a total water volume of 295 milliliters was consumed during the 10-second engine burn. It was found that the steam leaving the jacket quickly reaches choked flow conditions, so the steam vent was sized to allow sufficient mass flow when choked. The coolant delivery system was designed with only off-the-shelf components to reduce cost and engineering time. A plastic water accumulator tank with a gas pressurization diaphragm was used to hold the water, since it is low mass and low cost and meets the required tank volume and pressure. A solenoid valve is used to control the flow of water and was selected to be compatible with the planned electrical system on a future flight vehicle. The final system had a dry mass of only 0.759 kilograms and a total cost of $191.11, both of which are well within the total system requirements for cost and mass. All told, the design had a mass of 3.762 kilograms, which is well below the 5 kilogram design requirement. And our thermal models show it could easily fire for 10 seconds, meeting the other key design requirement. Unfortunately, the design materials cost did exceed the $1,000 requirement due to the high cost of titanium stock and the high cost of welding titanium, which must be done by a professional. However, the $1,300 material cost is still attainable within YGSP's budget. We can see that the majority of the mass of the system is consumed by the combustion chamber, which makes up 71% of the mass, and the coolant water makes up only 8% of the total system mass. This project proved that a chamber design using water cooling and phase change cooling is not only feasible, but can be cost-effective and have very low mass. Before a design can fly, though, the thermal and structural models used in this design must be validated by ground testing, as they made significant assumptions. Additionally, the graphite nozzle requires a manufacturing study to determine the actual thickness that it can be manufactured with due to the brittleness of the graphite. Thank you for watching. Any questions?